So today we're going to start talking about kinematics, or the study of motion. And we're going to talk about two things when we talk about motion. We're going to talk about speed and velocity, or speed or velocity, because they're not the same thing. In our little lesson here today, we're going to talk simply about speed. And they are not the same. Often they can be the same value as a scalar. They're not the same. We're going to start by talking about average speed. And average speed, which is, even though it's called speed, is notated with V of average, subscripted AV, is simply the distance traveled over an elapsed time. And it's independent of direction. So if I go 5 meters this way, 5 meters this way, that's 10 meters total of travel. And if I do that in 10 seconds, 10 meters over 10 seconds, 1 meter per second. It's independent of direction. And we call this a lot of times V average as the change in distance, delta L, over the change in time, delta T. And this is one of the formulas, first formula for your formula sheet. It is the equation, and it does not care about direction. 5 meters, 5 meters. It is independent of which directions those are. Often we make graphs of these situations. So we can have a case of uniform speed. Equal distance traveled in equal time. 1 meter per second, always the same. So again, if I make graphs of these situations, here I have a graph of distance in meters, 5 meters. And here's time in seconds over 5 seconds. 5 meters in 5 seconds, consistently the same, 5 meters per second. If I wanted to graph this then as a speed versus time graph, where I have time here in seconds and I have this and that would stay the same. And it would just be a horizontal line. Uniform speed just doesn't change. It's like going on cruise control on a flat road. You set it and it goes the same distance in the same time. And again, we're going to use graphs quite often, so you want to make sure you understand you can do these types of graphs. So the question I have is the following case on the board here: uniform speed. Time 0, he's at position. He has traveled 0 meters. He's at position 0, and he travels in one direction. So he travels 5 meters in 5 seconds. So just like the last graph we had, he traveled 5 meters in 5 seconds. Then he goes for another 5 meters, but it takes him 10 seconds. So is this uniform speed? No, he has a speed here and he has a speed there, but we can find the speed for the whole situation. The average in this case, he traveled 10 meters in 15 seconds. So I would call that 2/3 of a meter per second. But he has here where we know he went 1 meter per second, and if you look here, you know he went a half a meter per second, but his average speed for the 15 second span is 2/3 of a meter per second. This is not a uniform speed. And often when we think about speed, we're curious, how fast are you going here and how fast are you going here? So when the policeman stops you, you can say, oh, I haven't been speeding if you average the last 2 hours. He wants to know your speed right then. That is called instantaneous speed. And instantaneous speed is the speed you are going now. It's the speed you read on your speedometer in your car. And it comes from the idea that as you get the time smaller and smaller, and the change in distance smaller and smaller, and you actually take this time in the bottom denominator close to 0. Alright, and this is calculus. You can't divide by 0, but you can make it so super small it's basically 0. Our last graph was right here. Here's the 1 meter per second average speed. Here's the half a meter per second. And what we calculated on the last board was that it was 2/3 of a meter per second, right? That was the average in the red. We assume that. What we want to do is look right at the graph at any given point and find this value, the instantaneous, by shortening the time span so it's very small. And to use an example here I have a distance versus time graph where I put this in meters and I put this in seconds. And I have some point P on the graph. Now, again, if I was to do the average, it would not be there. But if we shrink that and get closer and closer, the way we do an instantaneous line is we draw a tangent line at that point. And we measure the rise and run of that tangent line. In this case, the units in the rise will be in meters. The units in the run would be in seconds. So if we found the slope of the tangent line, its units would be meters per second. And as that time got smaller and smaller to cause that tangent line, that would give us an instantaneous speed. This takes quite a bit of practice. We'll work on this in class. Again, it is the same formula, except we are making this smaller. Uniform speed works very nicely with the formula. This gives a good average for a situation. But as we go forward, we're going to talk about velocity next. And that is a much better thing because direction is important in velocity.